So what is algebraic structure? You already know. Basically, you have a set. With that, you have, okay, one or more than one binary operations. Like for example, this is algebraic structure. This is algebraic structure. This is algebraic structure. So in algebraic structure, you can have one or more than one binary operations. But in the GATE syllabus, we only have those algebraic structure which have only single binary operation. Okay, so let's move on. In the last class, we have seen what is the definition of binary operation. Binary operation basically means closed operation. Okay, and so I can say binary operation is same as closure property. So for, let's just take one example. Consider this example. Let's assume that you have this set. You have a set of natural numbers, and on this set of natural numbers, I am defining this operation. Okay, so this operation hash I am defining, and this operation is like this. What is this operation hash? This operation basically, what it will do, it will do the mapping. Can anyone tell me what this operation will do? This is set of natural number. So I'm defining one binary operation. So what this operation will do, this operation will map n cross n to n, correct? So n cross n, it will be mapped to n. Okay, so let me say that hash of these two elements, like hash of a comma b, hash of a comma b, that is same as a power b. Okay, so this is the operation. Now you can notice that this is the operation. So what this operation is doing, first you understand this operation. This is the power operation. So what this operation will do, this operation, for example, this will take 1 comma 1, 1 comma 2, 2 comma 1, 1 comma 3. Okay, for example, like this, these are the elements, and this is your set of natural number. So what this operation will do, this operation will map n cross n to n, this operation hash. So what is the image of 1 comma 1? Can anyone tell me what is the image of 1 comma 1? So that will be 1, because image of a comma b, that will be a power b. What is image of 1 comma 2? Image of a comma b, that is a power b. So 1 comma 2, image of 1 comma 2, that also will be 1. Image of 2 comma 1, that will be 2. Image of 1 comma 3, that will be 1. So that this is the idea. Okay, now remember this thing. So I can say basically this binary operation, we can think as a function. We can think this binary operation, we can think this is a binary operation. You can notice this is a binary operation. This binary operation you can think as a function. This you can think as a function. As a function. Okay. In simple words, if you want to understand, if you don't want to make this too much complicated, then in simple words you can understand like this, that you have this base set. So your base set is this is your underlying set, or I can say base set. This is your base set, this is your operation, this is your binary operation. Okay, and what this is doing, so if you have two elements, if you take a comma b, then what it will do, what is a hash b? A hash b is same as a power b. Okay, so like this you can understand this operation. So for example, what is 2 hash 1? 2 hash 1, that will be 2. Okay, what is 1 hash 2? 1 hash 2 will be 1. So this is the understanding of this operation. Okay, right? So this is the concept of binary operation. So this binary operation you can think as a function, you can think as a mapping. Okay, so anytime, remember this point, if anytime I give you that, consider this binary operation. Let's assume I give you a binary operation like this. If I give you a binary operation like this, that you have a binary operation from a cross a to a, then what it simply means, it simply means that, so okay, you have this binary operation from a from this binary operation you have from a cross a to a, and let's assume that hash of a comma b, okay, hash of a comma b. Okay, so what this means, first you tell me what this means, hash of a comma b. Hash of a comma b, this simply means a hash, right? So hash of this, hash of a comma b, this is simply nothing but a hash b. And I can say basically your base set is what? Can anyone tell me what is your base set here? What is the base set here? The base set is a. This a is the base set. So your structure is like this. So this is your structure. This is the structure. Okay, so this is the idea. Now let's move on. So tell me, which of the following is or are binary operation on set of natural number? What is the answer? Which of them are binary operation? Which of them are binary operation on set of natural number? Binary operation simply means closed operation. Okay, binary operation, it simply means closed operation. It simply means closure property. It simply means closure property. It simply means that this is mapping from n cross n to n. This is a mapping from n cross n to n. So which of them is binary operation? Yes, plus is the binary operation, correct. Minus is not the binary operation. Minus is not the binary operation. Why? Because you can very easily see that 2 minus 3, this is equal to -1, and this does not belong to set of natural number. This multiplication is binary operation. Division is not binary operation because 2 divided by 3 does not belong to natural number. And what about 5, 6, 7? What about them? What about them? 5, 6. These are Boolean. These are true false things. These are Boolean operations. These are Boolean operations, or I can say these are true false logical operations. These are logical operations. These are logical operations. So for example, remember, if you consider this like set of natural number comma equal, if you consider this is not your algebraic structure. This is not algebraic structure. This is not algebraic structure. Why this is not algebraic structure? Because if I give you two elements, let's assume I give you two elements, a equal to 2 and let's assume b equal to 3, then tell me what will be a equal b? What will be this operation? If you perform this operation, what will you get? You will get false. You will get false. And this false does not belong to set of natural number. This false you will get. You will not get a natural number, you will get a false. These are logical operations. These are not binary operations. Okay, so this is the idea. Now let's see this next question. So let's assume your base set I'm giving you. If your base set is this is your base set, then tell me which operation is binary operation. Your base set is this, t means true. Okay, so then which operation is binary operation? For example, can I say this operation is binary operation? Can I say this operation is binary operation? This operation? What about this operation? What about this operation? What about NAND? What about NOR? So which operation is binary operation? Tell me. Your base set is true. This is your base set. Base set itself is true. Now I can say, yes, this is binary operation. Correct? This is definitely a binary operation. Because true and true, the result is true. The result is true. This is also binary operation because true or true, the result is true. This is also binary operation. True implies true, that is true. This is also binary operation because true double implies true, that is true. This is not binary operation. This is not binary operation because true exclusive or true, that is false. And this is not in the base set. We don't have this in the base set. This, what about this? This is also not, because true, NAND true, this will be false, and this is not in our base set. And the same thing will happen for this also. Okay, so that's the idea. So answer will be 1, 2, 3, 4. Only these are the binary operations. Okay, so what is the definition of not closed? Can anyone tell me? What is the definition of not closed? If I say that as you have a set S, you have a set S, as set S is not closed, set S is not closed under hash. What this means? Under hash. If and only I'm asking not closed. So this means, it means there exists. This is very important. It means there exists A comma B. They can be same or different. They can be same or different. There exists A comma B. And this is important thing. There exists A comma B. Okay, such that A hash B does not belong to S. This is very important. This there exist is extremely important. Okay, this is very important. Basically, okay, there exist. So not closed simply means that there exist. There exists A comma B. You have at least two elements such that A hash B is does not belong to A. Correct? This is the definition of not closed. And let me tell you, many of you might be thinking that this is very easy. I know this definition. Yes, there exists. Okay, basically you have this set. This set is not closed. You have this set. What can I say? This set is not closed. Not closed means there are at least two elements. They can be same or different. They can be same or different. This A comma B, they can be same or different. Remember, this A, this B, they can be same or they can be different. The idea is that you have two elements same or different such that A hash B is not in S. So this is your idea of not closed. Okay, so tell me about this. Tell me about this one. This set 0, 1, plus. Is it closed? Is it closed? This is addition. This is your addition. I am talking about addition. This is addition. Is it closed? So this set is not closed. This set is not closed. Why this set is not closed? See, in this set, everything is fine. There is no problem with this set actually. Okay, in this set, everything is fine. 0 plus 0 is 0. Okay, this belongs to base set. So this is in the base set. There is no problem. Very good. 0 plus 1, that is 1. That also belongs to base set. No problem. 1 plus 0 is equal to 1. That also belongs to base set. But 1 plus 1 is equal to 2. And this does not belong to base set. So you can notice that this is enough. One scenario is enough. So I can say this is a not closed. So you can notice that three situations are in our favor. These are in our favor, but one situation is not in our favor. Okay, so this is not closed because there exist A comma B, 1 comma 1. There exist A comma B. And what are those? So here I can say not closed. Why these are not closed? So I can say not closed. Not closed because there exist A comma B such that A plus B does not belong to base set. And what are those A comma B? What are those A comma B? A is also 1, B is also 1. Okay, so you have two elements 1 comma 1 such that this A plus B does not belong to base set. Okay, let's see. So in the last class we have seen what is associative property. So tell me which of them is associative. One question from propositional logic. Which structure is associative? Okay, the question is about associative. So who is associative? Let's assume, yeah. Okay, let me give you the base set. The base set is a true comma false. This is the base set, true comma false. Then who is not associative? Okay, who is associative? So tell me, for example, conjunction, is it associative? Disjunction, is it associative? Implication, is this associative? By implication, is it associative? Exclusive or, NAND and NOR, are they associative? So which is associative? Which of them is associative? So tell me. This is the base set, true comma false. This is the base set. Then who is associative? We have already seen this. So you know that this conjunction is associative. Disjunction is also associative. This is also associative. This is also associative. These four things are associative. What about the remaining? Let us check. What can you say about NAND? Is this associative? Can I say this is associative? See, this implication is not associative. See, this implication is not associative. This is clearly not associative. This implication, this is clearly not associative. Why? For example, you can take false, true, false. You can take false, true, false. Just take this scenario. Okay, just to take this scenario you take. Now in this scenario, you can notice this and this. These are actually different. Okay, because what this will become? This will become true implies false, and true implies false. That basically means false, and false implies anything that is basically true. So this will become false implies false, and false implies false is true. So you can notice that they are not same. So implication is not associative. Okay, so this implication is definitely not associative. And what about NAND comma NOR? What can you say about NAND comma NOR? What can you say about NAND? This simply means NAND. So what can you say about this? So for example, if you notice A NAND B NAND C, if I give you this A NAND B NAND C, now is this same as this? Are they same? Tell me. What is this? This is A. This is AB bar. Basically, this is AB bar. Okay, so this is AB bar NAND C. Is this same as this? And this is A NAND BC bar. Finally, what you will get? Finally, this will be AB bar C whole bar, and this will be ABC bar whole bar. Correct? Are they same? They are definitely not same. You can just check it out. They are definitely not same. You can apply the De Morgan property and they will not be same. So this is not associative. This is not associative. Exclusive or this is associative, we have already seen. We will also see this in the digital logic. Okay, I will come back to this exclusive or. This is very important in digital logic. At that time I will tell you why this is associative, but you can check using the truth table. You can check. Okay, so you can solve it and you can check it out. But in the digital logic we will explore this. In the digital logic we will explore. Okay, so this we will explore in digital logic. This is very important in digital logic. Similarly, this NAND also we will explore. This NAND, NOR, these three things are very important in digital logic. Okay, let's move on. Okay, so in the last class we have also seen identity property, right? So tell me, which will satisfy identity property? Which will satisfy identity property? Identity property means identity element. So which will satisfy identity property? Your base set is true comma false. You have the base set which is true comma false. Then which will satisfy identity property? Tell me, will it satisfy identity property? Do we have identity element for conjunction? Do we have identity element for disjunction? Do we have identity element for implication? Do we have identity element for double implication? Tell me, do we have identity element for conjunction? This is our base set. Is there any identity element for conjunction? Yes. What is the identity element for conjunction? That will be true. True is the identity element for conjunction. For disjunction, identity element is false. What about implication? What is the identity element for implication? Is there any identity element for implication? Is there any identity element for implication? Yeah, implication does not have any identity element. There is no identity element for implication. See, false is not, see, E is not equal to false. Why? What is the reason E is not equal to false? Can anyone tell me? Identity element is not false. Why? Because false implies A. For example, false implies true. This is not equal to true. Similarly, E is not equal to true. Similarly, identity element is not true. Why? Because you can notice false implies true. This is not equal to false. So this is the idea. Yes or no? So identity element, false implies true. False implies false. Okay, so what should I give? I should give this counter example that E is not for identity element is not false because false implies false. That is not equal to false. That is not equal to false. Okay, so that's the reason I can say identity element is not false. And identity element is not true because false implies true. False implies true. That is not false. What about this bijection? This by implication. Do we have identity element for this? Yes, the identity element we have here. What is the identity element? The identity element is true because you can notice E equal to true will work. You can notice that E by implication false, that will be false, and true by implication true, that will be true. So you can notice that this identity element will work. This is your identity element, correct? Same question if I ask you for these operations, like what about exclusive or? What about exclusive or? What about NAND NOR? Do we have this exclusive or? Does it have identity element? Is there any identity element for exclusive or? Check E equal to false. For exclusive or, check E equal to false. For this exclusive or, can I say E equal to false will work? Will it work? E equal to false, will it work? Will this work? This will work, right? Because false by false exclusive or true, that will be true, and false exclusive or false, that will be false. So this will work. So this identity element will work, correct? So this is your identity elements. Yes, so this has identity property, correct? This has identity property because E equal to false will work. This E equal to false, this is going to work. And what about this NAND comma NOR? Is there identity element for NAND? For this NAND, check E equal to false. Is it identity element? This identity element will not work. This identity element will not work. Why? Because if you notice, what is false NAND false? What is false NAND false? This is not equal to false. So this will not work. And what about true? This will also not work because true NAND true. This is not equal to true. Okay. So for this NAND, there is no identity element for NAND. And similarly, you can check there is no identity element for NOR. Okay. For NOR also, there is no identity element. If you notice this NOR, then E equal to false will not work. Why? What is the reason E equal to false will not work? Because just check what is false NOR false. False NOR false, that is not equal to false. And similarly, E equal to true will not work. Because what is true NOR true? True NOR true, that is not equal to true. Okay, so that's the idea. So E equal to false will not work, E equal to true will not work. So the identity element we have for exclusive or, that is false. Okay, for this identity element will be E equal to false will work.